Okay, this is the 5-1 notes for Precalculus 2. This section is all about verifying trig identities, often called trig proofs. Okay, a lot of students will get very squirrely when they see this word, right? Basically, the idea is that along the way you have learned all of these trig identities. You've learned originally the reciprocal ones, which many of you knew coming into class, and then we have the quotient ones that are tangent and cotangent, sine over cosine, cosine over sine. And then you have the Pythagorean ones, which are the famous sine squared plus cosine squared equals 1. And then if you divided both sides of that equation by either sine squared or cosine squared, you're going to get the other two. So the key is that we need to be able to look at this, and we have to use these identities in order to prove that one side of an equation equals another side. So there are strategies involved with this for sure, but the couple things that are very important when it comes to this. You do not want to work on both sides at the same time. So just looking at number 1. So you can see that we have cosecant x times tangent x equals secant x. So what we do is we choose the side that is usually more complicated or more involved, and we start there and then work all the way until we get to the other side. So in essence, you can clearly see that the left-hand side, which I'll abbreviate by LHS, is equal to cosecant x tangent x. And that seems to be the more complicated side only because there's two things there, or two trig functions. So our goal is we need to manipulate these two trig expressions using our known identities in order to get a result of secant x. Essentially, trig proofs are a puzzle. That's all they are. They're a puzzle. But they're puzzles that students don't like necessarily because it's mathematical. Mathematics are involved, and trig, but we basically want to work our way to secant x. Now, there are tips along the way, so I'm just going to read this. It says, as we go through the examples in the section, there will be some pointers to assist with strategy for certain types of problems. For example, the first tip involves the idea of changing all trig functions to sines and cosines on the side you're manipulating. Okay, so that is a very good strategy, and even though we don't use it 100% of the time, we use it very often. So how do we manage that? So if you look at what's going on over here, if you look at cosecant x, we know what cosecant x is actually equal to because it's a reciprocal function. It's right here. We know that that's 1 over sine x, so we can replace cosecant x with 1 over sine x. We also know what tangent is, but we actually know two things of what tangent is. So if you look over at tangent, we know that it's equal to 1 over cotangent primarily, but we also know it's equal to sine over cosine. Now, normally, we're not going to be using much of this 1 over cotangent because what was the strategy of the tip? We really like to change all of these into sine or cosine. So this one right here actually accomplishes that for us. So therefore, we can go ahead and replace tangent with sine over cosine. Okay, so now it's all about simplifying. So if you look at these two expressions, if we went into, so let's do an aside here, our usual mathematical aside. So if I did, 2/3 times 3/5, well, a lot of students would multiply the top and the bottom and get 6/15. That's fine, right? But in reality, the easier way to do this is to simplify first. And what would you do? You would wipe out these 3's and then multiply to get 2 over 5. Well, we can do the same thing here. We actually have two fractions multiplied, and we have 2 sine x's. So we can simplify that and get a result of 1 over cosine x. Now, at this point, you should be keeping a very good eye on what we're trying to get to. So when we look at 1 over cosine x, we go, hey, we know what 1 over cosine x is equal. It's equal to secant x, okay, which is equal to our RHS right-hand side. So this is a trig proof. We worked our way from the left-hand side to the right side. It could be the other way around, depending on the problem. But we worked our way from the left to the right side and proved that this is equal to this. Okay, let's look at number 2. But before that, another tip. It says sometimes when verifying identities, you might find that trig functions are already all sines and cosines. So be on the look for some type of factoring in these scenarios. So why is this easy to find? Well, if you look at this problem, this looks a lot more complicated than the one we just did, right? We had a pretty straightforward singular. Now there's squares and cubes everywhere. But the key is if we went by our original strategy to change everything to sines and cosines, we would basically be done here. And if we look at any of the other formulas, yeah, we do have a square cosine squared right here and singular values. We could manipulate this and change this into a bunch of other things if we wanted to. But the key is that this is actually tailor-made for some type of factoring. So if we go through this, left-hand side is, we'll rewrite it, sine x minus sine x cosine squared x. Okay, so if you look at this guy, you basically say, okay, well, what could I do in this scenario? Well, this is kind of the same as saying something like, okay, if I have 2 minus 2y, okay, what would I do to factor that? I would take a 2 out and get 2 times 1 minus y. So this would be the GCF in this scenario, right? But that's not a matter. It's just basic factoring we're looking at. So if we go over here, we go, okay, it turns out that we have a sine x that both of these have in common. So we're going to factor it out. And we're going to get this as our result. Okay, clearly, this is not so far anything like this guy, right? Still doesn't look like that. Although we do have a sine going on here. So some of this is being smart about it in terms of the formulas, and others is using your intuition. So an interesting side part about this is if we're trying to get the sine cubed, and we know that this is already sine x, then that means that this should be equal to sine squared x. Okay, but do we know that? Well, look at the elements involved. We have sine squared, a cosine squared, and a 1 in this problem. So we're like, okay, well, if we go to our identities, we can clearly see that our original Pythagorean theorem has those identities, but it's not in this form. So we look at this and go, wait, can I make a 1 minus cosine squared out of this? So let's do a little bit of an aside over here. So if we have sine squared plus cosine squared equals 1, if we subtract cosine squared from both sides, we're going to get 1 minus cosine squared is equal to sine squared, which means we can replace any 1 minus cosine squared with sine squared. And by the way, that is another form of Pythagorean identity. It's just one that you just have to view, and this is something to be on the lookout in the future. And if we then multiply these two things together, we are going to get sine cubed x, which is equal to our right-hand side. So this would be the end of the proof. Okay, so moving on to 3, it looks like we have a new tip that actually expands for several problems. So let's take a look at it. You will find the fractions, so the dreaded F math word, pops up frequently when verifying identities. When adding or subtracting fractions, you must utilize least common denominators, the old school LCDs. This can also be a little tricky when dealing with trig. Okay, so if you look at this example in number 3, we have secant theta plus tangent theta equals 1 plus sine over cosine. So it turns out that we could do this. Both sides are complicated to me. So we could start on either side. It really doesn't matter. But if we're following the whole concept of adding and subtracting fractions and such like that, the strategy actually starts from the left side. So that's where we're going to start. So the left-hand side is equal to secant theta plus tangent theta. And note, if you looked at the first two problems here, do you see how we had x's as the variables? They might make a change to theta every once in a while. That does not affect the problem whatsoever. Just make sure that you have a variable after your trig values, because some people forget those or don't put them, and it's technically wrong. So if we look at this real quick, we can actually go, this is very similar to our first problem where we had cosecant and tangent. Well, we know what each of these actually is. So secant is the reciprocal function of cosine theta, and we know that tangent is equal to sine over cosine. Okay, you can clearly see that we have two fractions, and luckily, and it rarely will happen this way, by the way, is that we actually have the same denominator right now, which means we can condense these into one fraction and have 1 plus sine theta over cosine theta. Well, how did we know that? Well, just let's do basic fraction work here. So if we have, 2/7 plus 3/7, right? Then we know that we can combine the top and get 5/7, just like if we had x over 7 plus 4 over 7, we can combine the top and get x plus 4 over 7. It's all about condensing in order to get one single fraction. And if we do that in this problem, we end up with our right-hand side already, and we have a proof. Now note, we could have started with the right-hand side in this scenario and then split it into, it's basically the reverse process. We could have split it into two fractions and ended in the result. Okay, so what about number 4 here? So I'm guessing things are going to get much trickier from here. So if you look at this, immediately you probably notice that this left-hand side is more complicated. So let's write that out. Cosine x cotangent x plus sine x. If you look at this, again, we're sort of in the genre of, we're back to, just like we did here, to sines and cosines, exhausting that and making sure that all of them are in that form. So let's do that. So if we get cosine x, cotangent x, just as a reminder, head and back, cotangent x is right here. It's the reverse of, inverse of sine over cosine, reciprocal. You're going to get cosine over sine, just here, right? And we're going to get, we'll rewrite the sine x. Okay, so the result is a little bit different, actually. If we do the math, the multiplying, note that this is actually over 1. I actually want to put that in a different color. So note that this is actually over 1, right? So that's not what you'll get originally, but you'll realize that. So we're going to do cosine, but the key is nothing cancels out here. So if you look at the diagonals, there's no common values here, which means we actually have to multiply this out and get cosine squared over sine, and then we'll leave the sine x. Okay, so if we're looking at this right now, again, we have a fraction and a value, but we have an addition sign between them. If we look at what we're trying to prove right here, it doesn't look anything like what we have right now, and that's why trig proofs can be very stressful for students. But the key is that there is one single element right here. The only way that we're going to get one single element out of the grouping of what we have currently over here is if we actually condense these into one. The only way to do that is with a common denominator. Well, if once again we put the sine over 1, if we have in this scenario a sine and a 1 as the denominator, then that would be basically the equivalent of something like this in fraction talk. So if we have like 2, let's say, ninths, and then we have 5 over 1, then what's the common denominator? The common denominator is 9, right? So we would end up multiplying this by 9 over 9 in order to get 2/9 plus 45 over 9, and then we can add these together and get 47/9. Well, we're going to do the same thing here. The common denominator is sine. So what do? I'm going to rewrite cosine squared over sine. That doesn't need to change. I got the sine x, right, over 1 right now, but I need to multiply that by sine over sine so that I generate the denominator that I need. So multiplying this out, we still have cosine squared over sine x, but then we're going to get sine squared over x over sine. Now, some students lose their minds a little bit here, and they go, well, don't you simplify? Well, the idea here is you don't simplify, because the whole point of this is to get the common denominator, because we want that to be the case. So we end up with this. Now that they have the same denominator, we can do cosine squared x plus sine squared x over one single sine that has been condensed. Now, once we get to this point, we can look at this, and the denominator numerator should be screaming at you. Because what do we know from our very first Pythagorean identity right here? We know that sine squared plus cosine squared is equal to 1. So the entire numerator of this guy is just 1. So if we continue on with the proof, and yes, they are getting long, we're going to get 1 over sine x, which is a reciprocal identity for, you guessed it, cosecant x, which is going to be our right-hand side, and we have the proof that we need. Okay, so you might have noticed that number 4 was much more involved than number 3, or even some of the other ones we've done so far, right? So trig proofs can be more involved, and you want to be prepared for that. Normally, I do put different varying levels, skill levels on an exam to see how good you are at it and understanding. But in reality, this is definitely a skill that you want to become very good at. Number 5 would be an example on the high end of one of the more complicated problems, but it's extremely valuable to do because it's more common denominator work. So I'm going to write a little bit smaller here, only because this is going to take up some space, so you should do the same. So when you're looking at this identity, clearly the left side is a complete debacle. There's just a lot of, there's fractions and there's addition. So again, you can see on the right-hand side here, we need to be able to get to one single entity, so we have to combine these fractions. So I'm just going to save space this time, and I'm not going to write the original problem. Let's just talk about what we see up here. So if you look at these denominators, 1 plus cosine and sine, they basically have nothing in common multiple-wise. It's the equivalent of, let's say, doing something like 1/6 plus 4/7, right? So 6 and 7 have no multiples in common, so what do we do in order to get their LCD? We multiply them to get 42. So what do we have to do in that standpoint in order to make sure that they get to their common denominators? We have to multiply by a value of 1 so we don't change anything, but those values have to be the values that create the common denominator. So what do we get? We get 7 over 42 plus 24 over 42, and we can put that together and get 31 over 42. But generally, that is the process that we go through whenever we do common denominator work. So this time, since these two values have nothing in common, that means the least common denominator in this problem is actually going to be sine x times 1 plus cosine x. So that, even though it looks completely ugly, that is your least common denominator. So what do we need to do in order to make that work? Well, in order to get we'll start with sine x over 1 plus cosine x. We have to multiply this by the equivalent of 1 in order to get this denominator right here to turn into this. Well, what do we have to multiply? We have to multiply by sine x, But in order to not change this value, this entire fraction we're multiplying must be equal to 1. So that means this also has to be sine x. So then we go to our next value, 1 plus cosine x over sine x. What do we need to multiply by this time in order to get from sine x to this? We need to multiply by 1 plus cosine over 1 plus cosine. Okay, so there's a lot going on here. It looks incredibly ugly for what we have to go through, but we're just going to multiply it out. So remember, no simplifying here. We don't want to simplify, or maybe at the end, but not now. We want to create these common denominators. So we're going to get sine squared x over sine times 1 plus cosine for our first result right here. Then we're going to get plus there. Then we need this side, which is going to be this guy. Ooh, that's a colorful marker. We're going to get this side, which is going to be 1 plus cosine x squared over sine x plus 1 plus cosine x again. Hopefully you see that we have effectively, we found our common denominator. Because if you look at the two denominators, you're basically looking at the same thing for both of them. So you should be able to go over here and be like, all right, well, that means we have a full same common denominator of sine times 1 plus cosine. And now we just have to add the top two components. Well, the first component is sine squared, just fine. But the second component is actually a binomial squared. So just as a reminder, so if we did something like x plus let's say 5 squared. Remember, this is the equivalent of x plus 5 times x plus 5. So we have to remember that we have to FOIL here, right? So we would end up with x squared plus 10x plus 25 after FOILing, right? So now we have to do the same thing for 1 plus cosine x squared. That is going to be equal to 1 plus cosine x times 1 plus cosine x, right? So if we FOIL, we're going to end up, we'll do the full FOIL here. So first is 1, outside is cosine x, inside is another cosine x, last is cosine squared x. Okay, this is going to be 2 cosine x, so then we can write that out in our problem. So we're going to get 1 plus 2 cosine x plus cosine squared x. All right, so remove this all over there. So we basically have a whole new set of sort of a whole new equation or expression that we have set up here that we have to be able to manipulate. So what is this all about? Well, it's about, again, looking at this gigantic craziness. This guy, okay, I'm starting to like that color. This gigantic craziness and going, is there anything in there that you notice that we can actually simplify? Well, remember that you can't, like, for example, you can't cross out these two cosines right here because on the top, these are all separated by plus signs. You also can't simplify the sine x and the sine squared x. It doesn't work that way. So we have to use trig identities to simplify what's going on up here. So hopefully you notice that we have a cosine squared and a sine squared summed up here, which we know is 1. So what we're going to do basically is we're going to take this and this, and we're going to replace it with the number 1. So over here we get the number 1, which was our sine squared plus cosine squared, and then what was left over, which was 1 plus 2 cosine x. So replace sine squared plus cosine squared with 1, plus 1 plus 2 cosine x, and then let's repeat the bottom, which is sine x times 1 plus cosine x. And just a note on here, you never want to distribute this in any problem, because the goal is to get all these pieces together. Now, if you look at the numerator, we actually have like terms. We have a 1 plus a 1. So we get this. So rewrite everything else. All right, so now if you look at what's going on here, again, I know this stresses students out. we have to somehow get to 2 cosecant x, right? But you're looking at this and going, this is a gigantic expression, but a lot of times this is hard for students to see, but if you look at the denominator, there's actually a 1 plus cosine x, and if you look at the numerator, there's actually a repetitive 2 right here. So if you use a little bit of cleverness, you can factor out a 2 and get the following. Now we have two 1 plus cosine x's, which can now be crossed out to get 2 over sine x. 2 over sine x is equal to 2 over 1 times 1 over sine x. And 1 over sine x is, of course, cosecant. So you're going to get 2 times cosecant x, which is your right-hand side. So yes, you can see that this was one crazy proof that we had to go through. And yet, you very rarely get these in exam situations, but this is a great problem because it showed you a ton of different trig-proof strategies along the way in order to get to the end result. Okay, so the last problem in this section, let's again start with our strategies. It says, unfortunately, though, strategies aren't always one fits all when it comes to trig proofs. There might be problems where using any of the above strategies leads you down a frustrating path. Okay, so when doing these problems, if you just do one size fits all for every problem, change everything to sines and cosines, you could do that, but you want to be careful to always consider other trig proof or trig identities. So for example, some of the most forgotten about identities are these guys over here. Most students have the other ones sort of locked in their brain, but those are forgotten. You'll see there's a lot of squared trig functions that aren't sine and cosine. Some of them are, of course, dealing with a plus or a minus or something like that in there, but just keep these in mind when doing problems when you see squareds anywhere. So look at this guy. Literally every component is squared in number 6. So we need to look at this and go, well, what could we do right off the bat? So again, I'm going to skip the rewriting of this because it's big, just to save some time here. But hopefully right away, just like we have before, you see that there is a sine squared plus cosine squared immediately in the problem, which we know is 1. So if we simplify that, we're going to get 1 plus cotangent squared theta over 1 plus tangent squared theta. Okay, so this is the point where a lot of students would probably change, so tangent squared, for example, right? So tangent squared theta is essentially the same as sine theta over cosine theta squared, which is going to be sine squared over cosine squared, right? So a lot of students would, that's the worst S ever, we'll leave it though. So a lot of students would replace tangent squared with that, and then look at the disaster that you end up with. You have created fractions within fractions. Now, could a trig proof do that? Of course, but there's a good chance that if it's a problem in the book, they're not going to send you that in that direction. So maybe consider other alternatives before you get started. Well, there is actually a very clear alternative. If you look at 1 plus cotangent squared and 1 plus tangent squared, just look at your trig identities. Look at this guy right here. So, whoop and whoop. Look at that. Those are actually defined as trig identities, which means we can replace each one with cosecant squared and secant squared respectively in our problem. So that's exactly what we're going to do. So remember, again, 1 plus cotangent squared in this problem is equal to cosecant squared. So here, cosecant squared. And 1 plus tangent squared is equal to secant squared. Okay, once you do that, then you can play this the smart way. Cosecant squared, well, first of all, cosecant is 1 over sine. So cosecant squared is 1 over sine squared. Secant is 1 over cosine. So secant squared is 1 over cosine squared. If you divide by a fraction, then you multiply by its keyword is reciprocal. Right? We move down here. If we multiply straight across, we get cosine squared over sine squared. Okay, returning to our formulas, we know that cosine over sine is cotangent, which means cosine squared over sine squared is going to be cotangent squared. Okay, which is going to be our right-hand side. So again, definitely you can't keep this as a memorization thing where you do the same thing every time. Will you change the trig expressions, the cosine and sine a lot? Yes. But keep your eyes open for famous trig identities that might save you a lot of time and basically a lot less frustration will result.